Chapter is electrochemistry. General introduction. We have studied about redox reaction in class 11th and 12th. Redox reaction is a reaction in which one substance loses electron, undergoes oxidation, whereas another substance gains electrons, undergoes reduction. For example, in a reaction ZnS and plus USO4 aqueous, then after reaction then it forms ZnSO4 aqueous plus U in solid state. Zn has an oxidized to Zn2 positive, whereas Cu2 positive ions have been reduced to Cu. These reactions are accompanied by release of energy called chemical energy. By stable agreement, the chemical energy thus produced in a redox reaction can be converted into electrical energy. The arrangement is called the electrochemical shell or galvanic shell or voltaic cell. Conversely, a reaction may be spontaneous or ever and applying electrical energy to it, the reactions may become spontaneous. For example, no reaction takes place on melting NaCl, but on supplying electrical energy to molten NaCl, Na positive and Cl negative ions start moving towards the electrodes. Cl negative ions electrons to form Cl atoms under oxidation, whereas Na positive ions gain electrons to form the Na ions under oxidation. Thus, redox reaction occurs on absorbing electrical energy, which is otherwise non-spontaneous. The flow of current into the ion movement of ion is called electrolytic conduction. The phenomena is called electrolysis, and the arrangement used to bring about electrolysis is called the electrolytic shell. Electrochemistry is defined as the branch of chemistry which deals with the relationship between the electrical energy and chemical energies take place in the redox reaction. How chemical energy produced in redox reaction can be converted into electrical energy, or how electrical energy can be used to bring about a redox reaction which is otherwise non-spontaneous. Chemical changes involving production or consumption of electricity are called electrochemical changes. Thus, these three main aspects of study in the branch of electrochemistry are electrolysis, electrolytic conduction, and electrochemical cells, galvanic shell or volatile shell. Importance of electrochemistry is the subject of electrochemistry has great theoretical as well as practical importance. For example, first a number of metals such as Na, Ca, and Cal, and a number of chemicals such as NaCl2, F2, and are commercially produced by the electrochemical methods. Batteries, second as batteries and cells are used in the various instruments and other devices convert chemical energy into electric energy. Third is the sensory signals sent to the brain through the cells and vice versa. And also the communication among different cells are based on the electrochemical phenomena. Moreover, the reaction carried out electrochemically are generally energy efficient and less polluting, thus they are eco-friendly. Hence, their study is gaining importance to develop and new technologies. Now, in this unit, we shall take up the study of different aspects one by one. Electrolysis. Definition of the system used. Electrolysis may be defined as the process of decomposition of electrolyte by passing of electricity through its solution or molten fused state. The apparatus used for the about electrolysis is called electrolytic shell. It consists of a glass vessel in which the electrolyte in the form of an aqueous solution or in the molten state is taken. The two metal rods are dipped into and connected to the source of electricity battery. These rods are called the electrodes, and the one connected to the negative pole in the battery is called the cathode, and the other connected to the positive pole of the battery is called the anode. I have to see in right side electrolytic cell. One is the two rods are attached, and one is anode and another is cathode, and they are connected to a battery. Mechanism of electrolysis. The process of electrolysis can be easily explained on the basis of foundation theory. According to the theory, wherever an electrolyte, acid, base, or salt is dissolved in water or taken in the molten state, the electrolyte dissociates to produce positively and negatively charged ions. On passing current, the positively charged ions move towards the cathode and ions are called cations, whereas negatively charged ions move towards the anode and ions are called anions. On reaching their respective electrodes, ions can change their become neutral particle species. The cation accept electrons from the cathode to become neutral species, whereas the anion gives the electrons to the anode becomes neutral species. These oxidation occur at the anode while reduction takes place at the cathode. The conversion of ions into neutral species at their respective electrodes is called the primary change. The product formed as a result is primary change may be collected as such is may undergo secondary change to form the final products. Further, when the electrolysis of an electrolyte is carried out in the molten state, the products of the electrolysis are actually the substances obtained from the ions of the electrolyte. But the situation is not so simple when the electrolysis of electrolyte is carried out in the aqueous solution. This is due to the reason also some H positive or OH negative ions furnished by the slight ionization of water constituting when the magnetic current is passed, both the cations of electrodes H positive ions from water would move towards the cathode, while the anions of the electrolytes and OH negative ions from the water would move towards the anode. In other words, as a electrode, there are two different ions which can be discharged. Which of these two ions get actually discharged depends. First is upon their relative discharge potential, the potential at which one ion is discharged, and second is sometimes on which the material on the electrode used. Usually, ions with lower discharge potential are discharged in presence to those which have high discharge potential. Let us now discuss the electrolysis of some compounds in the light of the above mechanism. First, electrolysis of molten lead bromide in the molten state PbBr2 exists as Pb2 positive and Br negative ions on passing electrolysis. That is, Pb2 positive ions move towards cathode and Br2 negative ions move towards anode, and on reaching a cathode, each Pb2 positive ion picks up two electrons from the cathode and becomes neutral lead primary chains, and this is liberated at the cathode. On reaching each Br2 negative gives an electron to the anode, becomes a neutral bromine atom primary chain. Since bromine atoms are unstable, therefore the two bromine atoms combine to form a bromide molecule. Secondary chains, the bromine gas is involved at the anode. The reaction occurring two electrons may be Pb at cathode. Pb2 positive plus two electrons are called Pb. At anode, Br negative minus one electron is then form the Br. Br plus free radical plus Br free radical is going to form the Br2. Overall reaction Pb2 positive plus 2 Br negative, then after electrolysis Pb plus Br2 Pb Br2 after reactions Pb at cathode and Br2 at anode. The lead obtained at the cathode is in molten state. The electrolysis, second electrolysis of molten sodium chloride. Molten sodium contains Na positive and Cl negative ions. NaCl after equilibrium, then it form the Na positive plus Cl negative. On passing electricity, Na positive ions move towards cathode while Cl negative ions move towards anode. On reaching at cathode, each Na positive ions picks up one electron from the cathode and becomes a neutral atom. Thus, sodium metal is liberated at the cathode. On reaching the anode, each Cl negative ion gives an electron to the anode, becomes a neutral chlorine atom. Since chlorine atoms are unstable, therefore two atoms of chlorine combine to form a chlorine molecule. This Cl2 is evolved at the anode. The reaction occurring at the two cathode may be shown as the follows. At cathode, Na positive plus 1 electron and form the Na, and anode Cl negative minus 1 electron and form the Cl. So Cl free radicals plus Cl free radical then form the Cl2. Or a reaction N2Na positive plus 2 Cl negative, then after electrolysis then it form the 2Na plus Cl2. 2 NaCl after electrolysis 2 Na at cathode plus Cl2 at anode. The metal obtained at the cathode is molten state. Third is acidated water. Water is only weakly ionized and hence is poor conductor of the electricity, and but the presence of the acid makes it a better conductor. But this is because water filled with the sulfuric acid contains three types of ions: H positive, OH negative, and SO4 negative, produced as follows. H2 after that it form the equilibrium setup H positive aqueous plus OH negative. H2SO4 after reaction that will form the 2H positive plus SO4 negative. When electric current is passed through the oscillator to water, H positive ions move towards the cathode, OH negative SO4 move towards anode. Hence, this discharge potential OH negative ion is much lower than that of SO2 negative ions. For OH negative ion, the discharge at anode while SO4 negative ions remains in the solution. Similarly, H positive ion discharge at the cathode, the reaction occurring at the two electrons may be written as a cathode. H positive plus electron is then from the H free radical, then from the H2O. At anode, OH negative plus minus 1 electron, then from the OH for OH. After reaction, then it form the 2H2O plus O2. And the OI reaction is 2H2O after electrolysis, then it forms the 2H2 at cathode plus O2 at anode. For that is an aqueous solution of sodium chloride. Sodium chloride is of water energy atom. Water NaCl, then it forms the Na positive plus Cl negative H2O, then it forms the H positive plus OH negative. On passing electron, Na positive and H positive move towards the cathode while Cl negative and OH negative moves toward the anode. At cathode, both Na positive and H present near the cathode since the discharge position of a positive ions is lower than the Na positive ions, therefore Na positive are discharged in the presence of Na positive ions. H positive plus 1 electron then form the H free radical, H free radical plus H free radical then form H2. Thus H2 gas is evolved at the cathode while Na positive ions remain in the solution. At anode, both Cl negative and OH negative remain. Ions are present in the near the cathode, but discharge potential negative is lower than the OH negative, therefore Cl negative and discharge in the presence of OH negative. Then it forms the Cl negative minus 1 electron, then it forms the Cl free radical, Cl free radical, then it forms the Cl2. The Cl2 is evolved at the cathode and while OH negative ion remains in the solution. Electrolysis for the electrolysis of aqueous copper sulfate using inert electron and platinum electrode. The CuSO4 then it forms the Cu2 positive plus SO4 2 negative and H2 then it forms the H positive plus OH negative. At cathode, Cu2 positive plus 2 electron then it forms the Cu. The copper is disposed on the platinum electrode. At anode, during the aqueous CuSO4 solution, the Cu deposited at the cathode, O2 is liberated at the anode while the solution remains sulfuric acid. It may be noted that example 3 and 4 discuss about the electrodes as those which are not attracted by ions. Graphite and platinum, however, electrons are attracted by the ions, then the reaction taking place electrolysis are different. For example, let us consider electrolysis at a solution of copper sulfate and copper reactors. Fifth is electrolysis of electron aqueous solution of copper sulfate and using copper reactors. Now we discuss about the importance of electrolysis. Electrolysis has a wide application in industry. Some of the important applications are: first is production of hydrogen of electrolysis of water. Second is electrolysis attraction of metals like Na, K, MgCa and Al. Sodium, potassium are produced by the electrolysis of their fused chlorides, where aluminum is produced by electrolysis of molten aluminum oxide is mixed with chloride, discussed in previous chapter. Production of chlorine of electrolysis of aqueous NaCl solution. Fourth is manufacture of heavy water D2O. Fifth is electroplating and electrolytic refining of metals. 3.3 Quantitative concept of electrolysis and Faraday's law. The relation between the amount of substance liberated at the cathode electrode during electrolysis and the amount of current passed by was studied by the Michael Faraday. He put forward the following two laws, which are Faraday's laws of electrolysis. Faraday's first law of electrolysis stated the amount of chemical reaction, hence the mass of any substance deposited or liberated at any cathode, is directly proportional to the quantity of electricity passed through the electrolyte solution or melt. Thus, if W gram of the substance is deposited on passing Q coulomb of electricity, then Q W is directly proportional to Q, or Q W is equal to ZQ, where Z is the constant of proportionally and is called electrochemical equivalent of the substance deposited. If a current of 1 ampere is passed of 1 second, then Q is equal to I into T. If Q is equal to 1 coulomb or I is equal to 1 ampere, then T is 1 second, then W is equal to Z. Hence, electrochemical equivalent of a substance may be defined as the mass of the substance deposited when a current of 1 ampere is passed for 1 second and quantity of electricity is called 1 coulomb is passed. Faraday's second law of electrolysis, it states that when some quantity of electricity is passed through the solution of the different electrodes connected in series, the masses of substance produced at the electrodes are directly proportional to their equivalent weight. For example, for AgNO3 solution and CuSO4 solution connected in series, if the sum quantity of electricity is passed, mass of the Ag positives is equivalent weight of Ag mass of Cu depositive inverse of weight of Cu. Quantity concept of electrolysis. Consider the electrolysis of molten NaCl. Na positive plus Cl negative, then it form the Na plus half Cl2. Then we have Na positive plus one electron and form the Na. This means the one electron will produce one sodium atom. Therefore, passage of one mole of the electrons will produce one mole of the sodium. We again we start the reaction. Then Cl negative. Then it form the Cl plus one electron. Then do Cl negative who form the Cl2 plus 2 electrons. If two moles of electrons produce one mole of the Cl2. Similarly, looking at the reaction Cu2 positive plus 2 electron and form the Cu and the Al3 positive plus 3 electron and form the Al. We found two moles of electrons produce one mole of the Cu, whereas the three moles of electrons will produce one mole of Cl. The charge carried out by the mole of electrons can be obtained by the multiplying the charge present on the electrons with the Avogadro number. It is equal to the 1.602 into 10 raised to power minus 9 coulomb into 10 6.022 into 10 raised to power 23, and from the 96487 coulombs. This quantity of electricity is known as 1 farad. If it is constant, quantity is known as the Faraday's constant represented by the F. The approximate calculation for the is 96,500 coulomb mole inverse. Faraday's constant is 96,500 coulomb mole inverse. It is decided it if an electron are involved in the electron reaction, the passage of Faraday's of electricity will liberate one mole of the substance. In terms the electron may be this is the equivalent weight of the element is atomic weight of the element by a number of more electrons gained or lost by the atoms or in the elements. Two important result and the calculations. At 1 Faraday deposited 1 gram of equivalent substance, then electrochemical equivalent can be calculated from the equivalent weight. Z is equal to equivalent weight of the substance by May Faradays. Second, knowing the weight of the substance deposited W on passing definite quantity of electricity coulomb, the equivalent weight of the substance can be calculated. And equivalent weight is equal to W by Q into 1 Faraday. The quantity of electricity actually passed is calculated from the current and the time is follows. Quantity of electricity in coulomb is equal to current in 1 ampere and the time in seconds. You have to read these formulas. We have completed this formula in theory. Now next is topic is 3.4 conductance of electrolytic solution. Substances which allow electricity to pass through the known conductance, whereas substances which do not allow electricity to pass through are known as insulator. Conductors are divided into two cases. These those which conduct electricity without undergoing any decomposition, these are called the electronic conductors. Example metals, graphite, and certain minerals. As the same indicates, the conduction is in this case is due to the flow of electrons. Those which undergo decomposition when current is passed through them, these are known as electrolytic conductance or electrolytes. Solution of acid, bases, salts in water, fuse salts. In this case, the flow of electricity is due to the movement of ions, and electrolytic conductance is called ionic conductance. Electrolytes are further classified into main categories as strong electrolytes and weak electrolytes. Strong electrolytes are substances like strong acid. Example HCl, HNO3, H2SO4, etc. Strong bases. NaH and KOH, and most of the inorganic salt. These dissociate almost completely in the aqueous solution or in the molten state, and hence conduct electricity to a large extent. Weak electrolytes are substances like weak acid. Example is CaCOH or HCN or H2SO3 or H3PO3, and weak bases NH4OH, CaOH twice, AlO3, H3 thrice. These have low degree of dissociation and conduct electricity to small extent. Substances like sugar, ivory, etc. solution which do not conduct electricity are known as non-electrolytes. Factor affecting electrolyte conductance. The conductance of the solution electrolyte depends upon the following factor: nature of the electrolyte. Strong electrolytes ionize almost completely in the solution, hence conduct electricity to a large extent, whereas weak electrolytes ionize to a small extent, hence conduct electricity also a small extent. Second, size of the ion produced for the same solution. Greater the size of the ions or greater with the solution of the ions, combustion of the ions and solvents, less is the conductance. That is nature of the solvent and there is viscosity. Electrolytes ionize more in the polar solvent, hence the greater the polarity of the solvent, greater is the ionization and hence greater is the conductance. Similarly, greater is the viscosity of the solvent and less is the conductance. For this concentration of the solution, higher the concentration of the solution, less is the conduction. This is because in weak electrodes the ionization is less, whereas in strong electrodes the intra-ionic attraction are high in a higher concentration, while with the dilution in case of weak electrolytes ionization increase and in case of strong electrolytes intra-ionic attraction decrease and hence conduction increases. So the temperature on increasing the temperature, the dissociation increase and hence the conduction increases. Factor affecting melting metallic and electronic conductance. The electrical conductance through metals depends upon the following factor: nature of and structure of the metals, second nature of the whole valence electrons per atom, third is temperature decrease with increase of temperature. Difference between metallic conductor and electronic conductor, the main differences are following. Metallic conductor flow of electricity take place without decomposition of the substance. Second is flow of electricity due to the flow of electrons only. There is no flow of matter. The conductance depends upon the structure and the density of the metals and the number of the valence electron per atom. Third is the electricity conductance decrease with increase of temperature. This is because kernel starts vibrating, which produces hindrance in the flow of electrons. The resistance offered by metals is also due to the vibrating kernels. Electrolytic conductance, the flow of electricity takes place accompanied by the decomposition of substance electrolyte. Second is flow of electricity is due to the movement of ions, hence there is a flow of matter. Third is that the electrical conduction increase with increase of temperature. There is generally due to the increase in dissociation or decrease in the interanionic attraction. The fourth is the resistance shown by the electrolyte solution is due to the factors like intra-ionic attraction, viscosity of the solvent, electrical resistance and conductance. Every substance offers resistance to the flow of electricity to a small extent. This last exact value of the resistance is Ohm's law. It states that if the end of the conductor is applied to the voltage E and the current I flows through, and then the resistance R and the conductor is E by I. Current is generally measured in amperes, where voltage is measured in volt. If 1 ampere current flows through a conductor when a voltage of 1 volt is applied to the resistance and conductor is taken as 1 ohm meter. Then according to Ohm's law is equal to E by I ohms volt upon ampere, and SI base units is ohms is kilogram meter square into second cube ampere square. This is explained below. In it is seems metallic conductors shown all the electrodes also obey Ohm's law. It is obvious the substance which offers greater resistance will allow the electricity to the flow through. The result also from Ohm's law, according to which I is equal to I derivation to I by R. 1 by R. The reciprocal of the electrical resistance is called the conductance. It is usually represented by the G. G is equal to 1 by R. It is common practice or to speak the conductance of a solution rather than its resistance. Unit of the conductance is ohm inverse Mohs and Simons. Specific equivalent and molar conductance. It is observed that the resistance of is directly proportional to the length and inversely proportional to the area of the cross section, where rho is the constant of proportionality called specific resistance, and the resistivity depends upon the material of conductor. If L is 1 cm and area is 1 cm square and R is rho. So having zero resistivity and infinite conductivity are known as superconductors or already discussed. The second is equivalent conductivity. For comparing the conductors dense of the solution of different electrolytes, it is essentially that the volumes of the solutions depends upon the must contains the definite amount of electrolytes which give ions carrying the sum m total charge. The best choice is therefore the consider the solution having equal volumes and containing these corresponding grams equivalent weight. The conductance of the such a solution is called the equivalent conductance, and the equivalent conductivity of a solution at a dilution V is defined as the conductance of all the ion produced from the 1 gram equivalent of the equivalent dissolved in V centimeter square of the solution when the distance between the electrodes is 1 centimeter and the area of the cross electrodes is whole of the solution is contained between them. It is represented by the lambda electrolytes. Relationship between equivalent conductivity and specific conductivity. The equivalent conductivity of the solution is usually not found directly, but it is calculated from the specific conductivity. The relationship between electrolyte conductivity and specific conductivity may be obtained as follows. Consider electrical vessels to opposite walls 1 centimeter apart made seat. Case 1, suppose 1 centimeter solution containing 1 gram of the electrolyte is taken in the vessel. The conductance of the solution will be specific conductivity. Further, it 1 centimeter solution take place a gram equivalent conductance. Hence, the 1 centimeter cube of the solution containing 1 gram of the equivalent and the side of the equivalent conductivity is equal to the specific conductivity. Suppose 4 centimeter square of the solution containing 1 gram of the electrolytes, then we found that the 4 times of the specific conductivity. It is generally volume of the solution containing 1 gram equivalent of the electrolyte V centimeter square. Equivalent conductivity is equal to specific conductivity into V. In terms of concentration, we have found the lambda equivalent is equal to Kc into 1000 upon C equivalent is equal to Kc into 1000 upon normality. Note carefully that is above expression V is the volume into solution of a centimeters cube containing 1 gram of equivalent of the C. Units is ohm inverse centimeter square are the units of these. And the above formula units of the each quantity is lambda eq is Simon centimeter square equivalent inverse then is equal to k into 1000 upon normality. Next is molar conductivity. The molar conductivity of the solution is defined as the manner similarly to equivalent conductivity. Molar conductivity of solution is dilution. V is the conductance of all the ion produced from 1 mole of the electrolyte dissolved in V centimeter cube of the solution when the electrolyte is 1 centimeter apart and the area of the electrolyte is so large that the whole of the solution is contained between them. It is usually represented by lambda. Relationship between molar conductivity and specific conductivity is lambda m into kV into V, or lambda m is equal to Kc into 1000 upon C is into Kc into 1000 upon molarity. Now we read the 3.7 measurement of electrolyte conductance, specific conductivity, electrolyte conductivity and molar concentration. First is electrolytic conductance. Conductance is the reciprocal of resistance, and the conductance can be obtained by the measurement of the resistance, and the latter we have found the principle of Wheatstone bridge. You have to see in figure 3.5 and 3.6. 3.5 explain the principle of DC Wheatstone bridge method, and 3.6 two simple design of conductivity cell. First is A is filling type and B is the dipping type. It consists of 4 arms containing the resistance R1, R2, R3 and R4. R1 is the variable constant and R2 is unknown resistance with when null point is obtained where is no deflection of galvanometer G. R1 upon R2 is equal to R3 upon R4. Knowing the value of R1, R2 and R4 and R2 can be calculated. In finding resistance of solution in electrolyte, first difficulty to solution cannot be connected in the bridge like the metallic wire or any other solid connector. The difficulty is overcome by taking a special type of vessel such as the solution is present between the electrodes. This cell is used in called the conductive shell. It is made up of Pyrex glass and has platinum electrodes and fixed distance apart. A number of designs or conductivity cells are available. Two simple designs are formed in 3.6. The second difficulty in the measurement of the resistance and hence the conductance of the solution and reactide is different direct current is used. It causes electrolysis of the solution. As a result, the concentration of electrolytes near the electrolytes changes, and this result in the change in the resistance of the solution. These effects are called the polymerization effect. These to overcome this problem, an alternating current is used in the ideal frequency range is 500 to 5000 cycles per second is used. However, the alternating current is used. Ordinary galvanometer fails to detect the null point, hence the galvanometer is replaced by the earphone in the detectors. Further, to minimize the polymerization effect, the electrodes are coated with the platinum black. So some of these modifications required to use Wheatstone beads which are used. For the source of the direct current is placed by the source of alternating current, which is either an induction coil of a vacuum tube oscillator which is quite and coils symmetrically current. Second is galvanometer is replaced by an earphone. Third is electrodes of cells are coated freely with palladium black wire is used. You have to see the temperature for the measurement of electrolyte conductance, that is the figure 3.7. A suitable value for the resistance R is introduced by the standard resistance box, and when the editing contact J is used for the staged wire. And we found the Wheatstone base principle, then is resistance R upon resistance X is equal to resistance of wire AD upon resistance of wire CD, then is length of AD and length of CD. Then resistance X is equal to resistance R into length of CD into length of AD. Thus knowing the value of R, we balance electrolytes and calculated G is equal to 1 by X. Second is specific conductivity. Specific conductivity, or simply called conductivity, K is related to the conductance according to the expression G. K is equal to G into 1 by A. Thus, the conductivity of solution can be determined the measuring of conductance and the distance between the collectors and area of cross-section of each electrode, but the measurement of L and A is neither convenient or reliable. Wherever a particular shell L by A is constant, and this constant is called cell constant. Conductivity K is equal to conductance G into cell constant G. Third is equivalent conductivity. Equivalent conductivity is related to the specific conductivity. Lambda EQ is equal to K into 1000 upon C EQ. That is equal to the K into 1000 upon normality. Fourth is the molar conductivity. The molar conductivity is related to the specific conductivity according to the relation lambda m is equal to K into 1000 upon C is equal to K into 1000 upon molarity. In conductivity of water, the accurate result, the solution should be presently prepared by the purified where those and conductance is very small. Such water is called the conductive water. And to get a resistance of the electrolyte, the resistance of water is used, making the solution may be determined as subtracted from the resistance of the solution. And to solve these numericals based upon the theory. Next is variation of a conductance, specific conductivity, electron conductivity, and molar conductivity with dilution. In general, for weak electrolytes, strong electrolyte conductivity as well as equivalent conductivity and molar conductivity increase with dilution, whereas specific conductivity or electrolyte dilution decrease with dilution. The conductance of a solution is due to the presence of ions in the solution. The greater the number of the ions, greater is the conductance. As in dilution, more ions are produced in solution, so the conductance should also increase on dilution. The specific conductivity of an electrolyte falls with dilution because the number of the current carrying particles, ions present per centimeter cube of the solution becomes less and less on dilution. However, the increase in equivalent and molar conductivity or the dilution is due to the fact that is are product of specific conductivity and volume V of the solution containing the 1 gram equivalent or 1 gram molecule of the electrolyte, and decreasing value of the specific conductivity is more than the increasing value of V. The value of equivalent conductivity and the molecular conductivity increase with the dilution. Variation of molar conductivity with concentration for strong and weak electrolyte. Conductance behavior of strong electrode. The molar conductivity of strong electrode is found with concentration according to the equation lambda m c is equal to lambda infinity m minus lambda root c. As lambda is a constant depending upon A is the constant depending upon the type of electrolyte, the nature of the solvent, and temperature is the infinite limiting molar current. The equation is called the Debye-Huckel-Osmoger equation. Is a hold low concentration lambda m is the polarity against root c is a linear graph. Further, above curve obtains a strong electrolyte when there is only a small increase in conductance, and with the dilution there is a strong electrolyte is completely associated into solution, and so the number of ions remains constant. The higher concentration, the greater intra-ionic conduction related to the motion of the ions. Therefore, the conductance falls with increasing concentration with the decrease in the concentration with dilution, and the ions far apart. These therefore the intra-ionic conduction decrease with the indexing with the dilution is designed, and we have to see in right side the variation of a molar conductivity of strong electrolyte KCl Cl with a weak electrolyte CaCOH with concentration. Conductance behavior of weak electrolyte as a weak electrolyte dissociates to much lesser extent and compared to the large strong electrolyte. Therefore, the conductance of weak electrolyte is much lower than that of a strong electrolyte at the same concentration. This is follows. We have to see in some sample problems in CRT solved examples. Next is Clark's law. Clark studied the molar conductivity at a dilution for the number of pairs of strong electrolytes such as pair having common cations and anion. They can be calculated differences of these lambda not lambda infinity m values for each pair. A few results are given in 3.4. It is obtained from the differences between the lambda infinity m values for the each sodium potassium salt having the common ions and anion are the same. As representative of these in was similarly with difference in the lambda infinity m values for the each pair of salt, some different anions and some cations was to see in some values for the electrolytes for the different molar conductance. On the basis of the above observation, Glass concluded that each ions make a definite contribution to the total molar conductivity of electrolyte and different solution respective of the nature of the other ion of the electrolyte. The individual contribution of an ion towards the molar conductivity of the electrolyte is called molar ionic conductivity. Result Glass is in 1876 put a generation known as Glass law. The limiting molar conductance of electrolyte, molar conductivity and at infinite dilution is the sum of the limiting ionic conductivities of the cation and anion such multiplied with the number of ions present in the formula unit of the electrolytes. Mathematically, lambda na m infinity for the ax or by is equal to x lambda not positive plus y lambda infinity to minus. We have to find their values from this equation. Nuclear conductivity of electrolyte is infinite dilution in the sum of the two values are depending upon the cation and upon the anion. We have given some limiting molar conductivities of some common cation and anions. We have supplementary knowledge relationship between the molar conductivity and molar equivalent conductivity. Second is absolute ionic mobilities and their calculations. Our next topic is application of Clark's law. First is calculation of molar conductivity at infinite dilution for weak electrolytes. As already mentioned, the molar conductivity of weak electrolyte at infinite dilution cannot be determined experimentally. Firstly, because the conductance of a such solution is low. Secondly, because the dissociation of a such electrolyte is not complete even at a very high dilution. The molar conductivity of such an electrolyte at infinite dilution can be calculated using Clark's law. Consider the example of acetic acid CH3COOH and with characterized by Clark's law CH3COOH. I need to found that the lambda infinity, that is CH3CO negative, plus lambda infinity, that is H positive. Our formula is lambda what lambda infinity, that is acetic acid, is equal to lambda the infinity, that is CH3CO K plus lambda infinity HCl minus lambda infinity of KCl. First example is based upon the first application of Clark's law. Second is calculation of the degree of dissociation according to the Arrhenius equation. Theory of electrolytes dissociation. The increase in the molar conductivity of dilution entirely due to the increase in dissociation of the conductivity. The molar conductivity of infinite dilution being maximum because the dissociation is almost complete. Thus, the molar conductivity of solution is concentration C and lambda naught m, the molar conductivity of infinite dilution. And degree of dissociation alpha is equal to lambda c upon m by lambda infinity m. Relationship is hold good only the weak electrolytes. Third is calculation of dissociation constant of weak electrolyte. Knowing the degree of dissociation alpha, the dissociation constant of weak electrolyte like a CH3COH or NH4OH at concentration C can be calculated by formula K is equal to C alpha square by M1 minus alpha. These are the examples based upon the above equation. Fourth application is the calculation of solubility of spring-rich soluble salt. Such salt are AgCl, BSO4 or PbSO4 etc., which dissolve at a very small extent in water, are called spring-rich soluble salt. As dissolved they very little, their solution are considered as a infinite dilution. Further, as solution are saturated, their concentration is equal to the solubility. Thus, determining the specific conductivity and molar conductivity is solubility is equal to K into 1000 upon molar conductance of. Next, these are the example based upon the Clark's law. Key application पे. Next is galvanic shell, where an reduction is allowed to take place directly in a single beaker. It is found that solution becomes hot. For the example, zinc rod is placed in copper sulfate solution. So solution is found to be warmer in the solution produced according to the equation Zn S is plus Cu SO4 aqueous solution, and it forms the Zn SO4 plus Cu. Reduction. Similar results are observed when a rod of copper is placed in silver nitride solution. The reaction taking place is follows Cu plus 2 Az and NO3, then from the Cu and NO2 plus 2 Az. Then we conclude the whenever redox reaction takes place directly in a single beaker, chemical energy in the form of heat is produced by stable means. It is possible to bring about the redox reaction indirectly so that to convert the chemical energy into electrical energy. Here I have to see in the figure 3.9, that is the redox reaction take place in a single beaker. A device used to convert the chemical energy produced in redox reaction into chemical energy is called electrochemical or simply chemical shell. There also is galvanic shell or voltaic shell, the means of Lugix galvanic and Alexandro Volato, who were the first to perform experiment the conversion of chemical energy into electrical energy. And first is a redox reaction between Zn and SO4. Zn plus Cu SO4 then form the Zn SO4 plus Cu. Zn plus Cu2 positive then form Zn2 positive plus Cu. The reaction atom may be splitting. Zn is called then from the Zn2 positive plus 2 and oxidation half reaction. Cu2 positive plus 2 electron then from the Cu reduction half reaction. The first reaction is called the oxidation half reaction and the second is called the reduction half reaction. And we have a zinc rod is placed in the sulfite solution taking in a beaker. A copper rod is placed in copper sulfate solution, then is another beaker. Through connected a wire is two solutions are connected by salt base. Salt base and its function. Salt base is usable in containing concentrated solution of an inert electrolyte like KCl, KNO3 and K2SO4 and solidified Solution of waste such as electrolyte in agar-agar and galatine. An inert electrolyte is whose ions do not take part in the redox reaction and also do not react with electrolytes used. The function of the third base is to allow movement of ions from solution to the another. The mixing in the two solution and where the electrons allow the circuit to and in more have electrolytic concentrated solution of two halves. Meanwhile, start ways to first is to complete the electrolytic circuit by allowing the ions from solution to the another, and second is to maintaining the electrolyte in the solution. We have to see in the chemical shell based on the redox reaction that is Zn plus CuSO4 plus ZnSO4 plus Cu. Some important features of a galvanic shell is first the zinc rod is the oxidation take place in the anode. The copper electrodes is at which reaction take place in the cathode. Since the second is the since electrons are produced at the zinc electrode, the electrodes is the rich electrons and pushes the electrons into the external circuit and hence is designed at the negative pole. Third is the electrons flow from the negative pole to the positive pole in the external circuit. However, conventionally this current is said to follow the opposite direction. The oxidation of zinc into the iron produces excess of Zn2 positive ions in the left become similar in the reduction of the copper ions. The copper atoms leaves the excess SO4 negative. As copper is a copper from copper sulfate solution is deposited in the copper reactor and sulfite ions migrate to the other side. This evidence the weight of the copper rod will increase while that increase decreases the cell weight. And the galvanic shell also called the Dynein cell. Differences between the electrochemical shell and electrochemical shell. Electrochemical shell it is a device to convert chemical energy into electrical energy. Electrical energy is produced by the result of the redox reaction take place. Hence, the free energy is negative. In electrolytic cell, it is used to convert electrical energy into chemical energy. Electrochemical energy is supplied to the electrolytic solution to bring about the redox reaction as free energy change is positive. In electrochemical cell, it is based upon the redox reaction which is spontaneous. And the electrolytic cell redox reaction is non-spontaneous, take place when electrical energy is supplied. Electrochemical shell, two electrodes are usually set up in the separate beakers. Electrolytic cell, both the electrodes are suspended by the solution or melt of the solution in the same beaker. Electrochemistry, the electrode take place in the two beakers. Electrolytic cell is taken in one beaker. The electrodes taken as different metals. Electrolytic cell may be same or different metals. To set up this cell is salt, base, porous pot is used in the electrolytic cell. There is no salt base in case.